Hello Physics 35 students, this is Mr. Hofstad. Today we're going to look at some other types of miscellaneous or non-conventional circuit components. Well, the first couple are pretty ordinary, but then we'll get into some of the more obscure types. So, first of all, we got an ideal ammeter, similar to our notion of ideal gases or ideal springs. This is a theoretical, not actual thing, but it could be a pretty good representation of a really good ammeter. So in a perfect world, our ammeters would have zero resistance. And this is necessary for an ammeter. If we can remember, ammeters are components that are analyzing current, right? Current represented by capital I. And if we want to measure the current of a circuit, we don't really want to affect that flow of electrons, right? Because current is all about the flow, the speed of electrons. So by having a zero resistance ammeter, we're not going to be slowing them down at all, and we'll be measuring as close to original current flow as possible. We won't be disrupting the current, right, with an additional resistance from the ammeter that we need to throw into the circuit by necessity. In order to read the current flow, we need to throw the ammeter directly in the circuit, but if we have a high resistance on that, it's going to actually change the amount of current that's experienced, right? And it's going to provide potential difference drop. So ideal ammeter has zero resistance, just like Howard. An ideal voltmeter, so voltmeter, this one's a little more obvious, has volts, right? I guess ammeter is kind of obvious too, because the unit for a current is an amp. Current, or the unit for potential difference, electrical potential difference, or EMF, is a volt. So we're measuring volts, and in order to have a perfect voltmeter, we're going to want infinite resistance. So it's exact opposite of an ammeter. We want to make sure that no current is going through the voltmeter. And there's a little bit of a difference between voltmeter and ammeter. Voltmeters will always be in parallel with your circuit. That's why with infinite resistance, none of the current will actually break away from its regular circuit and join up with our voltmeter. Right, it'll all continue. I'll show you in a second what I mean. It'll continue on its original path. Whereas an ammeter needs to be in series with the circuit, because as soon as we introduce parallel avenues for electrons to flow, we're going to have to think about Kirchhoff's first law, and we're introducing new junctions and we're splitting our current. So voltmeter is in parallel and our ammeter is in series, parallel. All right, so not a bad idea, even though these notes do cover lots of the stuff, to take a look at the textbook that you guys have access to and do some of your own reading on this material. This stuff is less about the mathematics, more about the understanding and the concepts. So doing your own reading can be really beneficial to that type of learning. So even just using the internet is a good way for you to get some extra knowledge on these three special electrical components that we're going to be looking at pretty briefly. So on top of your extra reading, here's a nice brief walkthrough of these components. The first is a potential divider. So this is a very simplified, the most simple version of a potential divider that we can have, where this voltage in is going to come from our battery, and we're looking at here conventional flow coming out of the positive, the bigger side of the cell, and back into the negative, because conventional flow is how an imaginary positive charge, test charge, would travel through. All right, so we're measuring the voltage between the negative terminal of our battery and a point between our two resistors. So our two resistors here are named top and bottom. You could just as easily name it 1 and 2. But the point of a potential divider is to determine the voltage, right, across a resistor, right, or between two resistors. And we're always going to stick to this formula. So voltage out is what is measured. You can think of it like a voltmeter, right? If we had a voltmeter here in parallel, right? So a voltmeter again would have infinite resistance. So we would not actually have any of our current, our conventional current flow breaching into here. If this is an ideal voltmeter, the current will encounter infinite resistance here. It won't be able to flow at all, right? We'll have a backlog and it will all flow through that second or bottom resistor. And that's essentially the point of having a voltmeter, right? As soon as we have the current breaking off, we need to then look at these resistors in parallel, and we're going to be doing a lot of damage to this actual reading of the voltage across this resistor. So we'll always take the bottom resistance, so this guy, and divide it by the total resistance of both resistors, multiply that fraction or that ratio by our input voltage, which will be created by our electrical cell or our battery. Okay, so we can only do it using a point after the first resistor, before the second, and then a second one after the second. So it always needs to be a potential divider needs to be around our final resistor. All right, so if we were to solve this using that same formula, we know we would have to place our potential divider here first. All right, so this would be our V out. And we have two resistors, a top and a bottom. They're both equal. And you can see, if we think back to our formula, we're going to take resistance of the bottom, which is 10, divided by resistance of top plus bottom, which is 20. So we have 10 divided by 20, or 1 over 2, multiplied by our input voltage, which is 9, will equal our output voltage, 4.5. Half of 9 is 4.5. Right? So we had to look at this guy first. And once we have, so this could be our voltage or V out. Once we have the voltage of this potential divider, right, across this second bottom resistor, we can then use our second Kirchhoff law, our loop. So if we're just looking at this as our one and only loop, we have positive 9, right, minus this unknown. That would be our V top, minus 4.5, which we calculated using our potential divider. And that all needs to equal 0. So we know that this top one also has to be 4.5. But we can't use our potential divider formula for this one because there's no resistor on top of it, right? There's no extra resistor here. But sometimes you will have that, right? Okay, so quick example here. We have 12 volts input. Our bottom is 120. So we're going to find our V out, which is this guy here, measured by our voltmeter with infinite resistance, is going to be equal to the resistance of the bottom, 120, divided by top plus bottom. So 120 plus 80 gives us 200. And multiplied by our 12, we get 7.2. 7.2 volts. That one belongs here in this voltmeter, that potential divider. And again, we could use Kirchhoff's second law, right? We have positive 12 minus our unknown, minus 7.2. So that all needs to equal 0. 12 minus question mark minus 7.2 has to equal 0. Right. So we get 4.8. Right. So when this equals 0, our question mark or our unknown potential difference across this resistor becomes 4.8 volts. And we would just use that in there. Okay. A little more complicated. We can do this now with more than one using the same formula and the same method, right? We would start with this guy here. I guess you could technically start here and work up. I'm going to choose to start here. So we have our bottom as 6, our top as 2. So 6 over 8 is our ratio times the 6 in. So I'm going to skip the math there, kind of just verbally set it. So 6 over 8 times 6 gives us 4.5. Right, and we could also create a second one from here. Actually, we need to combine these two in series. I did that wrong. Let's start over, because we always need to start at the negative part of the battery. Right, we need to connect this negative part, so that needs to be 1 point of our voltmeter, and then the positive is going to be between two resistors. So we can combine those two. Since they're resistors in series, all you have to do is add them. So we can create this R bottom, which is 10. R bot is 10 ohms. And we're going to measure across here. So we have 10 divided by 10 plus 2, or 10 over 12 times 6 gives us 5 volts. Right, and again, we could look at this part here without them combined, right? Use C and D as our 2 points for our potential divider. And then we would combine these to become the top, which is 8. So our second voltage here, right across this 4 ohm resistor, right, break it apart from this combined bottom. Now we're looking at a combined top versus our 4. So our bottom is 4 divided by our 8 times 6. 4 over 8 times 6 should give us 3. 3 volts here. I'll come back to this one. Sorry, guys. All right, potentiometer. This is a different electrical component where we can change the resistance. Kind of think about it as being able to slide our voltmeter right across here. So depending on where we're looking at it, we're going to have either more resistance on top or less on bottom, or more on the bottom, less on top, right? So if we positioned it here versus where it is, we're going to have a lot more on top than on the bottom, right? And that tells us that the voltage across here, right, with lower bottom, higher top, is going to be smaller voltage across here, right? Or we could look at it all the way up here, right? And then we have a little bit on top, lots on bottom, so we would have our bottom being a much bigger number and our top plus bottom, or we could call that total, being smaller. So that's going to be a larger voltage out. So potentiometer, right? Think of it like an adjustable or like a sliding resistor, right? And you can change this contact point of our parallel voltmeter, right? And the output voltage will vary accordingly. And our next type, so this one you can often be heard as a rheostat, right? And it's like what we would have with our dimming lights. Can I just type? No, that would be too easy. Okay, so this would be a rheostat, R-H-E-O-S-T-A-T, rheostat is another name for a potentiometer or something very similar to it. And it is essentially how we get dimming light switches or anything like that, anything that you can adjust on kind of a scale, right, where it's not either off or on, but you could slowly increase. I guess even like different levels on a fan could almost be this idea, but that's more quantized, discrete intervals, where a potentiometer or a rheostat is a continuum, right? Light dependent resistors. So I don't know if any of you have little lights set up in your garden that go on when it's dark, but anything that, right, turns off or on, or even, I don't know, some night lights in your house that only go on when it's dark, those are all powered using these light dependent resistors. So it's the special component or device that has a resistance that varies depending on the amount of light that's on its detector surface. All right, you'll see this symbol if it comes up on a circuit representing a light dependent resistor. So they usually have high resistance in the dark and low resistance in the light. And when you throw it in our circuit and we get our output voltage using our, not our potentiometer, but our potential divider, there we go, then we'll find the output voltage when we have light outside, right, or a small resistance. It's going to be small because the bottom is the light dependent resistor. So if you have a small bottom resistance, then we're going to have a small voltage, right? Those are directly proportional. And if you have a really big, then we're going to have an increased output voltage. So when it's shady, we have a high output voltage, and that's why you can often have these turn on lights when it's dark out. Okay, so big thing about light dependent resistors, they're light dependent. That's pretty self-explanatory. And if you want to know more about them, right, you can remember that in the light they have low resistance, which results in a low output voltage across them. And when it's bright out, they have a high, which results in a high output voltage across them. Right, and we can always do the math just using our bottom over bottom plus top times our input voltage to calculate output voltage. All right, our last fancy component or device is a thermoresistor or thermistor. I don't know how to say it properly. I'll go with thermistor. This one has to do with temperature, like a thermometer, like thermal. It has to do with heat, right? So the root word thermal means heat. So it's a resistor that decreases its resistance with increasing temperature. And this has to do with our kinetic molecular theory and what we talked about in topic 3, where as you add heat, you add energy, right? Kinetic energy. And that would mean we have more moving particles, and more moving particles means more moving electrons. So the electrons are able to flow easier through it, and you'll see the resistance decrease as the temperature increases because those electrons are able to flow easier and faster and all of that. They're facing less resistance from this device. So I guess everything has this to some extent, but if you use the right materials, you'll see a really dramatic difference. And yeah, here's just a diagram of the thermistor. This is our circuit drawing of it. So it has the line through it and up. I will give you a sheet with all of the ones, but these are also given in your IB data booklet. So if you come across circuits with weird components that you don't understand, take a look at that formula sheet and you should be able to figure it out. All right, this is all for our special components. Let's look at the specialist component of all, the cell, electric cells, and the AA meeting. I love Kirkland batteries. They're not the best, but they're the cheapest. So there's a lot of chemistry in this we're not going to touch on because you'll do that in chemistry. We'll just look at the physics behind these cells, these electric cells. So if you ever hear talk of a primary cell, that's our non-reusable, non-rechargeable batteries. Okay, that's as simple of a definition as you can get. The reasoning to that is because the electrochemical reaction was actually the chemical reaction that's actually producing our voltage and in turn our current cannot be reversed, right? It's a one-way reaction. It can't easily be reversed, so maybe you'll get a little bit, but not enough to be a feasible rechargeable battery. So we don't need to get too much into the chemistry. This is just an overview of what's happening. We always have a cathode and an anode, right? And here they're showing the electrical electron flow rather than conventional flow, which is more usual for chemistry. And since these cells kind of fall into the branch of physics called chemistry, it makes sense to show this diagram with electron flow. So we have electrons leaving the zinc, and I always get this wrong, but I'm going to say zinc anode. So electrons will leave and they'll flow through this voltmeter, which will tell us how much electrical potential difference, or actually technically EMF there is, right? Electromotive force between the cathode and anode, and we'll get this continued flow of electrons, right? And this buildup of potential difference and a voltage across the battery. So here as we all know, looking at a battery, the side that pops out is our positive side, and electrons are negative. They're going to be attracted to the positive side, and they're going to flow out of the negative side where they're repelled. So I was right. The negative is the anode, and that's where the electrons are coming out. And then we're going to have them giving away their energy, right, to this light bulb or this load, right? We're going to convert chemical to electrical energy here, and this electrical energy is going to be converted into heat and light energy inside the light bulb filament. The electrons are just the carriers of that energy. They're going to be depleted of that energy and returned to the cell to be recharged by this electrochemical reaction, where we have a whole bunch of chemistry happening that we're brushing over because this is a physics course. Okay, we're looking at discharge characteristics quickly. So ideas of how batteries deplete over time, how they give off or discharge their energy. These characteristics, right, for a good battery are going to have this really steep drop at the start and a nice flat continuous drop for the majority of its life. So it'll lose its initial value, which is quite high, very quickly, and then it will have a stable and constant value for the majority of its lifetime, which is good. That's what we want batteries to be, right? Nice and constant, nice and even keeled until they are at the end of their life, and we have a rapid decrease to zero, and it discharges completely, right? We'll have no more electrochemical reaction occurring inside of this battery or this cell. Oh, and we have this capacity here is microamp hours. Okay, so it's current times hour versus voltage. So primary cell are non-reusable, secondary cells are reusable. These are our rechargeable batteries that can be reversed by running a current into the cell with a charger to recharge it. So this will actually regenerate the chemical reactants, right? So once our cathode and anode become depleted by running a current through it the opposite direction, we'll have them being restored to their former glory. So secondary cells are not super ideal. They're definitely getting better, especially with lithium ion, because these older versions of secondary cells have quite a high self-discharge, where the chemical reactants inside the battery reduce the energy available. So they're actually using up their reactants on their own without actually producing the energy that we want them to, right? They're a little more unstable in that way. They won't last as long, and we get a lot of waste energy from the chemical reactions occurring inside them. So this is an older kind of idea, but we're getting better with lithium ion. But if we were stuck with these older rechargeable, right, they would have a much shorter lifetime. You'd be recharging them far more than you would be replacing primary cells. So this is important. You probably will cover this in chemistry if you haven't already, but it is in our curriculum to talk about how we would recharge these secondary cells. So as it's discharging, so this is when it's working normally, it's producing its potential difference across the cathode and anode. We're getting electrons flowing from the anode across the load back to the cathode, right? They'll swim across actually and continue this journey, right? And eventually we won't have enough of our lead and lead oxide to continue this. I think this is the components of a regular car battery. So once it's depleted, we're going to run a current in the opposite direction to the discharge, right? So we're going to force electrons through by attaching an external source, right? That's strong enough and powerful enough just like a car battery charger, to force the electrons against their discharge flow, and we're going to get different cathode and anodes momentarily, right? And they're going to be absorbing all of the components that are in our dilutate, more chemistry stuff that we don't need to focus on, and they'll rebuild themselves essentially. That's as simple as we can think about it. So that once this electron flow from the outside source is removed, right, we now have a functional cathode and anode again, other way, anode and cathode, and we can continue this discharging. This is, yeah, extra chemistry stuff. If you want to think about doing rechargeable batteries for a chemistry IA or something like that, you can dig more into this, right? But not super essential to our physics idea. The big part about the physics side of this is having to run electrons opposite to their discharge flow using an external source, right? And that will in turn regenerate our cathode and anodes, reverse the reaction for a short time so that we can continue it later on. All right, our last idea of the day, the internal resistance within a battery, because so far we've assumed that every cell we've looked at, every power source has no resistance inside of it. This is not actually true. There's actually this difference between potential difference, which we remember is the kind of voltage across components within a cell, and that'll be lower across a cell than the EMF should be across the cell. Remember, EMF is the electromotive force, and that one is always measured across a cell, and it's the amount of chemical energy converted to electrical energy. So to visualize, we're going to kind of break up our cell into the part that is producing our EMF and the part of it that is acting as a small resistor within the power source. So far we've been thinking of all cells as just being this right half of our visualization aid here, where it's just a perfect cell where all of the EMF is actually distributed to our circuit. But what's actually happening is we have this power source, this EMF, and even within the battery there's resistance experienced, and we are dissipating some of that energy before it ever gets the chance to leave and power the rest of our circuit. Here we're looking at conventional current, because we have our positive side here and our negative side here. So the positive is leaving the positive and coming towards the negative. This is conventional, not looking at electron flow anymore. That's the hard part about circuits in physics, that we switch between conventional and electron flow. All right, so the internal resistance here is symbolized by the little r. Capital R is the resistance of the circuit. Here's our equation that we can generate using Kirchhoff's second law. So second law, remember, is the loop law, the potential differences across the loop, the voltage drops. So first we have the source, which would be positive, and that's going to be our EMF, which is our epsilon symbol here, symbolized by epsilon. Then we're going to have the current go through the resistance of the circuit. So we'll have a voltage drop of I times capital R, and we're also going to have the current drop, or the voltage drop inside of the cell, capital I, little r. And we can factor out our current and get our EMF is equal to the current times, in brackets, the resistance of the circuit plus the resistance of the cell, or the internal resistance. So hopefully this is pretty easy math for you guys. You're all smart. You can all do this. Here's an example. We know the EMF is 12 volts, internal resistance is 1.5 ohms, and it produces a current of 3 amps. We want to find the potential difference across the cell terminals, right? So cell terminals would be related more to the internal part of it. So we need to find the portion that is current times our resistance of the circuit. So EMF is measured in volts, right? It's equal to, or the voltage of the circuit, which is what we're looking at, across the potential difference across the cell terminals would be equal to the current times the resistance of the cell, right? So that'll be our voltage we're looking for, plus the current times the internal resistance. So we can rearrange it to solve for this potential difference across cell terminals. So that would be our EMF minus our current times our internal resistance of this cell, 1.5. So we get 12 volts minus our current of 3 times 1.5, giving us 7.5 volts. That's actually being measured across the cell terminals. So we're losing all of this 3 times 1.5 to our internal resistance. So we're losing a whole 4.5 volts to the internal resistance in the cell, which is pretty big. Yeah, this is just a recap of our voltmeter being infinite resistance. We can measure the EMF of a cell when there's no current flowing because we're not dissipating or losing any energy due to the internal resistance. So if you just hold a voltmeter directly to two sides of a battery, you'll actually be able to measure the EMF, and you can compare that to the measurement that we're losing once we actually connect it to a circuit, right? And then through that, you can calculate internal resistance. All right, that's it for today. Good luck, everybody. Bye. Let me know if you have questions.